Good afternoon, everyone. There's everyone. Took a minute. So welcome to the final presentations for Nanoscience Lab Session B. My name is Dr. Rita Blake. I am the Manager of Education here at the, well, not here, but there, at the California Nanosystems Institute at UCLA. I am also the Administrative Director for this program, as well as a few other programs, summer programs that CNSI also runs, amongst other educational initiatives that we do. So just to give you guys a quick background for those of you who are unfamiliar, CNSI, again, is the California Nanosystems Institute. We were opened in the early 2000s by then Governor Gray Davis when California was still very wealthy and had lots of money to spend. So it was an institute that was opened at a time where he decided, Governor Davis decided that he wanted to open up what were termed California Institutes for Science and Innovation. So there are 4 different institutes that he opened that were all dedicated to looking at the next biggest, greatest thing in science. So CNSI is one of them, and it's devoted to nanoscience. So we have 4 sort of main things that we do at CNSI, all again around nanoscience. One is fostering team science. So CNSI is in the center of what's called the Court of Sciences. So CNSI has faculty membership from all over the Court of Sciences: physical sciences, life sciences, School of Medicine, School of Engineering, all of whom come to CNSI to do interdisciplinary research based around nanoscience. Another big platform is entrepreneurship. So we have an incubator space up on the 6th floor for people who are working in this nano space and decide that they have an idea that's potentially worth commercializing. We also have core technology centers where we have machines that are dedicated to looking at and making the smallest of nanomaterials possible. We also have a focus on education, which is my field. So we do a lot of work in K through 12 outreach, public outreach, educational summer programs such as this one, amongst many other things. So that just gives you a brief sense of what CNSI is and what CNSI does. So more specifically for this program, there are a lot of people that made this possible and that I have to acknowledge before we start. One of whom is our faculty PI for the outreach program, the faculty professor, Professor Sarah Tolbert. She's our faculty director. She's also a professor in the Department of Chemistry and a researcher at California Nanosystems Institute. She will be joining us shortly and will also be here to very gently grill our students and ask the really good, hard-hitting questions about their projects. So just wanted to take a moment to acknowledge her. I also need to acknowledge the current and also previous leadership at CNSI. So Dr. Jeff Miller, who is our director at CNSI, our executive director, Sonia Luna, and the previous education director for CNSI, Dr. Jiaming Chen, all of whom were really instrumental in both facilitating this program, providing infrastructure resources, and in the case of Dr. Chen, providing a lot of help for me because this is my first year running the summer program. There's also a lot of people behind the scenes that have really been instrumental in helping this program run. Lucas Lee, our AV IT manager, Nikki Lin, special projects director, Kevin Quinones, our events manager, and Mark, who is sitting right behind all of you and is very helpfully allowing us to live stream this final presentations onto YouTube, which means that not only can people watch these remotely, but you can also all watch them after they're done. So you can watch these whenever you want. Isn't that great? So no pressure. One other person that I definitely have to acknowledge because she is my other brain for this summer, and I definitely couldn't do any of this and coordinate it all this well without her, Dr. Elaine Morita, who is our program coordinator. So Elaine, thank you so much. Another big thank you, and another piece that's instrumental again to getting this program to happen is all of our instructors and our counselors. All of our outreach and education efforts at CNSI are pretty unique because almost all of them are conceived and facilitated by UCLA graduate student researchers under the direction of Dr. Tolbert. So they are actually all the ones who over the course of many years, created these labs, honed them into being very well-oiled machines that are really, really good at getting out very specific concepts related to nanoscience. They also gave their time throughout this week, both as many of them as instructors and some of them as counselors. So they also are completely instrumental to having this program run, so I wanted to give them a shout out. And I couldn't list them all by name because there's too many of them to fit, but they're all very, very important, so thank you all. And then last but certainly not least, thank you to all the students and to all the parents for being here today. And it's sure to be a nice culmination to what was a very, very intense week for all of the students and for me too. So just to give you a quick sense, parents and students, to reflect on what you guys did over the course of the week. This is kind of the everyday schedule that they were doing. So every morning they had an experiment that they did, each touching on a different part of nanoscience. Then in the afternoon, they would be treated to a guest lecturer doing research within this specific topic that they were studying in the morning. And then they would have what are called demonstration labs. Actually, Sarah, I'm gonna redirect you to that seat because it's got a mic for you. So then every afternoon, they had an afternoon activity or series of activities that gave them sort of broader connections to what the activity was in the morning, to really go more in depth into some of the unique details about visualizing the things that they made, sort of advanced topics within the things that they made and that they looked at. So really getting more sort of an in-depth look. And then today, of course, is their final presentations. And with these final presentations, what they did over the course of the week, what their homework was, it was quite interesting. It was for them to take what they learned and try to visualize the concepts behind that experiment using a visual metaphor. So they had to draw a picture without being literal and without using any of the terminology that they learned for the experiment. They had to try to draw a picture that would be able to explain the experiment to somebody outside of the field, so to their siblings, to their parents, to their friends, to their grandmothers, to their grandfathers, to people who are just completely unfamiliar with the topic, which is more of a challenge than you might think. It sounds really easy. It's really, really not. A really good test of someone's understanding of a topic is trying to teach it, because when you're trying to teach it and you can't use, a term that you memorize that relates to the topic, you can't hide behind not knowing a thing. So it's a really, really interesting test of their knowledge and of their communication skills. So for these presentations, what they've done is each team of 3 has gotten a drawing of somebody else. So they got a drawing that was not made by any of them, and they had to look at the drawing, try to figure out which experiment it was representing, try to figure out the metaphors that were being used, and then they're going to try to analyze those images and give some feedback on what they did really well and what extra concepts could be added in also. And 2 of our teams, I'll have to give them a little extra shout out, 2 of our teams actually didn't even have a full evening to do the homework. 2 of our teams actually did it on the supercapacitor experiment that they just did this morning, which means that right after they finished the experiment, they created their drawings, and then the 2 teams switched, and they had very, very little time to actually look and analyze those drawings. So extra shout out to those teams, because again, they've had the least amount of time to sit with the material and the least amount of time to draw and to learn the other team's drawings. So we'll give them extra kudos as they come up, but just wanted to acknowledge that very briefly. So with all of that being said, we'll just get right into the presentations. So for parents to know and to remind the presenters, so every team is going to have 5 minutes to present, and I will time everyone, so please try to keep your presentations to 5 minutes because we have 11 of them to get through. So 5 minutes to present, and then 5 minutes for Q&A from the audience, which will be roughly probably 1 question from Dr. Tolbert and then a couple of questions from everyone else in the audience. We have a laser pointer for everyone, so it's this top green button here that you can use to point at things on the screen. And please, when you come up here, please talk into the mic. It's much easier to hear you if you use the mic, and definitely for the live streaming people, you need to use the mic for them to hear you. So please, please, please talk into the mic, and I'll remind you if we can't hear you in the mic. Dr. Tolbert also wanted to come up and say a couple of words before we get started. So let's give a nice round of applause to Dr. Tolbert.
I just want to add my welcome to the parents who are here. I'm Sarah Tolbert. I'm the faculty director of this program, and I'm a professor in the Department of Chemistry and Biochemistry and also in material science. And to all the students who are here, I hope that you have learned a lot about nano concepts, Now, for all you parents, here is your job. So, as you heard, what their job is to do is to take these pictures. And I should say, it seems like drawing a picture is sort of a 5th grade homework assignment. But in reality, we as scientists do this all the time. When we are creating a presentation and we're trying to explain our research to other scientists, I sit there with my graduate students and I say, how are you going to make a picture of this? Because it is a picture that other people will understand. And so this is actually fundamental to what scientists do. But what's harder here is we said it can't just be a picture for other scientists, because if it's for other scientists, it's pretty easy, because then they share a whole base set of knowledge with you and you can draw pictures of things that scientists recognize as science concepts. No, we have to make it harder. Now you have to use that same idea, capture the essence of a topic, and make it accessible to non-scientists. And I told these guys, if I had you write a 5-page essay on each experiment, it would have been easier. And I think you probably agree. It would have been easier. Okay, but so now parents, here's your job. So they're getting this picture that they did not draw. They need to explain the picture, and in the process, they need to make all of those science concepts clear to you. So they need to use this picture that's not theirs as a vehicle for making a science experiment accessible. I don't know how many of you parents are scientists versus non-scientists. Particularly the non-scientist parents, you are the ones who need to ask questions. So their job is to make these concepts accessible to you. And if you don't understand any of it, you got to raise your hand and say, I didn't get this part. So explain it again, because always in this situation, if you don't get it, it's not your fault, it's their fault, right? Because their job is to make it clear to you. Okay, so we definitely need your participation. And I will just add that if you don't ask questions, I will ask more questions. So if you want to save your children from my questions, you'll ask a whole bunch of questions. Okay, so if people don't get to ask your questions, or if your explanation is cut short, please understand it's not that you're not a phenomenal presenter and a phenomenal scientist, but we have 11 of these, and I guarantee that by the 11th presentation, people will be just dying to get out of their seats, and we don't want the 11th group to not have a receptive audience. So we are going to try to rush both presentations 1 through 7 and presentations 8 through 11 so that everyone's not happy at 1 and miserable at 11. Okay, so parents and other audience members, remember, it's your job to ask questions. The more the merrier. And let's get started.
All right, thank you. All right, so with all of that said, Team 1, if you would like to step up. And yes, let's give all our teams a nice round of applause. And yeah, there's 3 mics, 1 for each of you, and remember to talk into them.
Hello, everyone. I'm Daniel Brown. This is Kevin Nune. This is Blake. We'll be discussing lithography today. So, cell phones, computers, TVs, and any new age technology requires the use of transistors, integrated circuits, or microcontrollers. These technologies are like really small, some the size of a few nanometers, with current transistors being the length of 13 nanometers in size, compared to a hair, which is 60 to 120 micrometers in size, which micrometers is 100 times larger than nanometers. So you could just imagine how small these really are. And there are a lot of them too. There are up to 3 billion transistors in current technologies, such as everyone's iPhone. These nanotechnologies are made using photolithography. Photolithography is a process that uses UV light to etch patterns into matter. Using photolithography, scientists are able to etch patterns that are nanometers in size. So without photolithography, we wouldn't be able to use all the technology we have today.
All right, so I'm going to be explaining to you guys the photo that's up on the screen. Oh, yeah, the pointer. It's a good idea.
Bad ankle, but you can.
All right, so starting with those first two pictures over there, it should, like, as you can see on the first picture, there's like a couple of particles on the nail, like dirt. And what those first two slides are really trying to show is that there's often times, like on the nanoscale, like things that we don't realize that with the naked eye, like dust particles that can really get in the way of the process of photolithography and really mess things up at nanoscale, even though we don't really realize them. And then moving on to the third slide, that shows the application of the like the coating of the material that they're trying to create the pattern of on the substrate. The substrate is the base of like what you're trying to make. Like for example, if it's a circuit board, it'll be like the very bottom, and then like the base that's applied onto the nail. And the third slide would pretty much be like the metal, the conductive metal for the wires and the for the electrical currents. And in the third picture, you can see that they're using a magnifying glass to create a more sharp image. That's a commonly used practice, like to use like microscope lenses to or microscopes in order to create more intricate patterns on things on the nanoscale. So moving down to the slide down there, that shows the masking of the material with the coating, and what that does is that creates a part of the material coating that is uncovered and exposed to light, which is essentially how they mark up the material that's being etched onto the substrate. So what happens is after they lay down the coating and they show the mask, which is reveals the parts that are getting removed. They, as you can see, like the pattern in the next slide, it gets like shown after you use the etching fluid, which pretty much eats away at whichever part hasn't been covered. And moving on to the last one, that's pretty much the finished product of the photolithography process. And for these two final slides, it shows that without the use of like magnification and more intricate processes, like the patterns couldn't be as detailed as they are at the nanoscale. A lot of common practices for this, for the really small intricate patterns, include using light that isn't UV light. Like for example, sometimes electron beams are used in order to create more intricate patterns. Because electrons have a shorter wavelength than regular light, you're able to create more detailed patterns.
Okay, so we have some additional concepts that we'd also like to discuss that weren't included in the illustration, but they're also part of our topic. So one of these is Moore's Law. It was first coined by Gordon Moore, who was the co-founder of Intel. In 1965, and it's less of a law and more of an observation. Basically, his observation was that the transistors in an integrated circuit will double every 2 years. So this kind of exponential growth in the transistors and our integrated circuits kind of shows how much our technology has progressed through the years. Another concept that's related to photolithography is a SEM, which stands for Scanning Electron Microscope. So in normal light microscopes, we use photons, which are basically light, in order to see small things. But for electron microscopes, we use electrons. These electrons are higher. So these electrons, they have a shorter wavelength than normal light. So that way we can be able to see smaller objects. So yeah, that.
Any questions?
Okay, I'll start this off. All right, so in explaining your picture, so I should point out that I have zero base knowledge of what you would do to fingernails if you so desired to do so. So I don't know what the process that's being described here is. But so you went through and you talked about cleaning and you put down a base layer and then aligning your mask. But then I'm actually confused on the figure, and I don't know if you guys really explained it, in terms of the bottom left two figures, what happens, you are, I guess, removing part of that bottom layer, but then between the middle and the right, it goes from light to dark. So what is the process and how does that relate to photolithography in the middle two bottom figures?
Oh, okay. So the reason it goes from light to dark is because the what you see on the left is the light part is the masking that they use to in order to keep the rest of the nail hidden, and then once they remove that, then that's like the pattern is revealed, and then like there's no more masking.
So what's the color, the two colors in the middle bottom?
On the left, it's the mask that they applied to keep the rest of the nail hidden, and then on the right, it's like the full nail without any masking or anything on top of it.
And the nail polish?
Yeah.
Okay, I guess I don't see how that goes from the process flow along the top, but maybe the artist will help us eventually. But other people should ask questions first.
So, I know we had, during the lithography session, we had places where we would add on different levels of, I don't know, different layers, and if we were somehow able to remove them, so how would that be shown in this picture?
This picture is more representative of like the single layer photolithography that we did in class. But if you wanted to do an even more layers, like you could put another layer of like the base coating, like in the third panel over there, and then you could put another mask over it, and then like continue the process over the original.
So another question. So there's a concept, so like as we talked about, no drawing ever can capture all aspects of a picture, and it's not supposed to. So one of the aspects, there is a key aspect of your photolithography experiment that this one chose not to capture. And can you talk about what that key aspect is, and maybe think about a way you could put it in? Relating sort of to the name, photolithography.
So one thing that there's nothing of is light, or specifically UV light, which is what is used in photolithography in order to mark up the base layer on top of the substrate. So one thing I think that could have been used is on the bottom left panel, after the coating on top of the mask, they could have had like a light dryer, which is like something I know my sister uses. So yeah, they could have had like a little thing that you put the nail under that like puts light on it and heats it up and makes it like dry quicker or something like that.
Will the artist behind this drawing also stand up for a minute so we can acknowledge your work? Nicely done. Did you want to add any comments as to what they were talking about or explain the drawing a little bit? But they got everything else in your drawing otherwise? Pretty much. Yeah? Great. All right. Well, thank you. All right. Next group.
So for all groups, when you're explaining these, do start with the base assumption which is not necessarily true, but use it anyway, that your audience has not the slightest knowledge of this concept. And when you're explaining the cartoon, explain it in such a way that somebody who's never heard the word before can understand the whole topic.
Hey, my name is Renell. This is Noah. And that's Jared. And we'll be presenting hydrophobic and hydrophilic surfaces. So hydrophobic surfaces hate water. They want to repel it, while hydrophilic surfaces is the opposite of that. They love water and want to be attracted to it. An example of a hydrophobic surface in nature would be the lotus leaf. On top of the leaf, it's hydrophobic because it wants to, the water removes the dirt, which obstructs the leaf from sunlight. This topic is important because we can use this information to develop material that is waterproof, such as a raincoat. And Noah will explain the drawing on top.
Hello. So, first of all, this first picture here would represent hydrophobicity, showing how this woman here, wanting a man who's muscular and has a lot of money, is repelled from this man who has neither. And this here is hydrophilicity. This man here has one of the things that she requires, and so she stays with him, but she's not exactly satisfied. Here we have super hydrophobicity, which is pretty much just the extreme version of this. She has one of the things she needs, but she's repelled. And here, super hydrophilicity, which is her being extremely attracted to this man because she holds all of her requirements. So what we believe here to be is the muscles represents in a surface to be nano roughness, which it's nanoscale roughness. It's pretty self-explanatory. It's the roughness of a surface at the nanoscale level. And the money here, we believe, is representative of the chemical functionality of the surface, which is basically what the surface secretes. And so these two things equal hydrophobicity, but the one thing we noticed about this picture is that it's sort of flipped on its head, which Jared will explain.
Yes, as my friend Noah explained, the last picture with the man with muscles and money is actually kind of inverted, because considering hydrophilicity involves no chemical functionality and no nano roughness on most occasions. Nano roughness and chemical functionality would actually facilitate super hydrophobicity, which is actually what the picture on the bottom left would represent. So that's one thing about the image that was a little confusing or could mistrack someone. But other than that, some other things that the image doesn't quite explain is the angle of contact for what would be the water, because contact angle is important because it shows how exactly hydrophobic or hydrophilic a surface is. And to be more specific, super hydrophobicity or super hydrophilicity can be determined by if the contact angle is either less than 15 degrees for super hydrophilicity or more than 150 degrees for super hydrophobicity. And one other thing about the image that could have been refined a bit more is how this technology, hydrophobicity and philicity, could be applied to in real life. For example, there are lots of things nowadays that use hydrophobicity and philicity, both in the natural world and the world that we humans live in. For example, we have a lily plant, which uses which uses super hydrophobicity to clean itself whenever water lands on it, because the water doesn't stick. so it just rolls off the leaf and while cleaning the plant. And yes, that's basically it for hydrophobicity and hydrophilicity. Thank you.
Do you have a question?
I actually just want to start with 2 comments, and then we can go into questions. So the first is a request to everybody, just in terms of the language that you use, and that is to say, every single cartoon that one draws, by definition, captures only some aspects of the concept. And we expect that, and that's part of the whole process. And so it is important to discuss what aspects of the cartoon are not, of the science, are not captured in the cartoon. But they are not things that are left out or failings of the cartoon. They are limitations of the analogy. And so please really think about the language that you use, because it's part of the process that a cartoon will always have limits. And the drawer knew that when they were doing them, and they just, some concepts can't be incorporated into every cartoon. So please think about language when you're doing that. The other thing I just wanted to comment on, and then let you guys maybe say a little bit more, is that for the interaction of water with any surface, there is always a chemical interaction. It is not that sometimes there is and sometimes there isn't. There is always a chemical interaction, and sometimes it's a favorable chemical interaction, and sometimes it's an unfavorable chemical interaction. But all 2 chemicals always have an interaction. So maybe you could say a little bit more about the picture in light of thinking about it with that concept. I think the cartoon can be well explained within that picture. Go for it.
I don't.
So yeah, speaking of chemical functionality, I do admit that, yes, like you said, every surface does have some degree of chemical functionality.
Maybe I ask a different way. Is money a favorable or an unfavorable chemical functionality?
Money in this case would be a favorable chemical functionality if you were looking at it from the point you wanted more hydrophilicity. But yeah, like you said, in real life, chemical functionality would more normally, like you see, like on human skin, oil, it would most benefit hydrophobicity in that case.
But that's an unfavorable chemical functionality.
Well, yes.
So I think you're exactly right. In this picture, money maps onto a favorable chemical functionality. And so then I think you can explain all 4 pictures in terms of the presence or absence of a favorable chemical functionality and nano-roughness.
Yes, and that's one thing I think we pointed out, or we would like to point out, that in this case, hydrophobicity and hydrophilicity, the things that would make something hydrophobic or hydrophilic are kind of inverted, because as you see, the super hydrophilic image, the one with both favorable traits, is actually implying nano-roughness and chemical functionality being the...
And favorable chemical functionality.
Correct.
Which is what gives super hydrophilic surfaces.
Oh, correct, yes. No, would you like to add anything?
Other people have to ask questions. I've said enough.
All right, any questions? Yes, actually, we can.
So we had 4 pieces of copper, which would be the surface, and then there was 4 types. One was added to a chemical called decantyl.
Okay, so in general, you guys, for all of you, just like forget the chemical names and just like say what it does.
Okay. Which and we also use what is it?
I think they just want a very simple description of what is the sample that you made? What did it look like? Because this is the big concept, but nobody right now knows anything about what did the sample look like. Started with copper, what'd you put on it? What were the base ideas of your 4 samples?
So one was with DC was super hydrophobic, where like we add drops of water on each top of the pieces of copper. So one was completely was flat, kind of, and that would be the super hydrophilic, and then another drop of water on another piece of copper was hydrophilic. It wasn't completely like flat, and then another piece of copper was hydrophobic. It was we measured the angles of the drops with a protractors to determine if it's hydrophobic or hydrophilic. So the normal piece of copper had was a contact angle of greater than 90 degrees, so it was hydrophobic. And then the last piece of copper had a contact angle of greater than 150 degrees, which is would make it super hydrophobic.
One of the other of you just tell them a little more about what the sample was? Just like the super short version.
Okay, so in essence, the sample was basically just a piece of copper that was coated in this kind of silverish metallic material that created a degree of nano roughness, which, as we discussed, made it gave it a favorable trait of
Rough silver, that's all?
yeah,
Then
in essence, rough silver.
Treated it with what?
And then we treated it with 2 different chemicals. One was DCM, like you said, and the other was
What was their property?
and in essence, their properties were to either enhance hydrophobicity or hydrophilicity. And that, combined with the nano roughness, would either make it super hydrophobic or super hydrophilic.
Yes.
As the next group comes down, the artist behind this one, would you please stand up and we can acknowledge you? Very nice. Is there anything that you would like to add to what they were saying? Very nice. Thank you. Okay, next group.
Good afternoon, everyone. My name's Aisha, this is Dani, and that's Max. And so in everyday life, one thing we use all the time is energy. Whether it comes from fossil fuels, from natural gas, or solar energy, it's all around us constantly. Currently, we highly depend on the burning of fossil fuels for our energy source. And that is really taking a bad effect onto our environment. So this past Tuesday, we got to do an experiment with solar cells, and we learned about how they work and how they can help us reduce the amount of fossil fuels we're using. So we built dye-sensitized solar cells, which are very inexpensive and not as effective as silicon solar cells that are used in commercial use. So they were very inexpensive. They were kind of kitchen ingredients. We used raspberry dye to coat the cell that would help absorb the light that would actually cause a reaction. And so, yeah.
Okay, so this drawing is analogous of one of the solar cells that we made, and one of the most important things to start off with is this kind of, this cycle that it goes through. A solar cell is a repeating cycle with electrons flowing through it, and in this drawing, the electrons would be, as you can see, the carts. And the artist in this drawing actually did a poorly built solar cell and a well-built solar cell. So in the poorly built solar cell, you can see that these carts are falling off and they can't get all the way to the top. This is an important concept where we need to balance voltage and amperage. Amperage is how many electrons flow through a circuit, and voltage is the difference between the energy levels of each electron. And in a poorly built circuit, many of the carts can't get to the top. This is analogous to electrons not being able to reach the higher energy levels in order to absorb the light. In a well-built circuit, there is a good balance between both the amperage and the voltage. Furthermore, I'm going to talk about the different parts of the solar cell that were shown in this drawing. So we had a lot of different parts. Some of these were not able to be included, but two of them that were are, this is analogous to the sun. It's what powers the entire roller coaster, and it's what allows the solar cell to actually function as it would. And this provides the energy that is then absorbed by the dye. And there is no dye in this analogy. However, here is where we can see wavelength dependency in the absorption of light. This is certain wavelengths of light cannot be absorbed by our solar cell that we made. This is because they aren't the right color or are simply reflected off of the solar cell instead of being absorbed and made into energy. This shows that not all wavelengths of light can be used in order to make a functioning solar cell, and this must be taken into account when actually creating one.
Hi. So I'm going to do a little bit of constructive criticism right now. Have a pointer? Thank you. All right.
Use different words.
Do some applauding and...
We're going to talk about the limits of this analogy.
We're going to talk about the limits of this analogy. All right. So one of the limits that we were talking about is, so there was a concept between different types of wavelength. And one of the concepts we learned is like, how am I supposed to see something if it's not the same size? So it's kind of, the analogy that someone gave us was like, if you had a blind person that had one of their poles, if you had a beach ball at the end of it, they could sense a car, but they couldn't sense a crack in like the sidewalk or something, which is obviously a problem. So up here, this is actually two different types of electric current, which means that down here, this cycle was not able to work as efficiently because it wasn't the right amount of current or the amount of energy that needed for this to run. And up here, this was a good electric current for the system to be able to work. So that was good. There was certain things that were part of our solar cell experiment that we had to do. There was really fun things called iodine and titanium, and what all of this would do was we actually needed to concentrate the electron energy and find a way to actually use it. So those were not exactly super representative in this particular figure, which personally was really hard to do even when I was doing it. So that was something that I really hoped we could find a way to put on here that'd be really helpful. And that was my time, so I guess questions?
Okay, I'll start. All right, so as you said, this picture is describing basically the path of the electron in your solar cell and how you pump it up and how you have to have the right wavelength matched. Okay, so what are the nanoscience concepts that are not in this solar cell, and how could you, in this drawing, and how could you imagine putting them into this drawing?
Do you want to take it or you want me to take it?
Okay, I can take it. So one thing that we did not really touch on, that was not touched on in this drawing, was the methods for controlling the deposition of the film of the solar cell. It kind of doesn't really show how it can break down in the dye-based solar cells that we created, and it's not quite as efficient in. It doesn't maintain efficiency as a silicon commercially manufactured solar cell would.
Okay, so that's good, but my specific question is, this is a nanoscience program, and you made this solar cell in a nanoscience program, so where's the nanoscience in this solar cell? And hint, it's the answer to the same answer as everything else.
So we actually have particles that were inside our raspberry dye, and what happened was there's a really big balance in trying to get surface area to a point that's big, but without too big, so that you want to like maximize the surface area and minimize the area that the cell actually takes up. And what this does, it has more ports so that the dye can actually combine to these nanoparticles, that's a word, nanoparticles, and this allows more electrons to be excited, so it actually makes the process way more efficient than it otherwise would be. So nanoscience actually helps us make this process work so much better with a lot less. Was that good?
So now your question is, imagining, what would you do to this drawing to maybe put that nano concept in here? Not that I have an answer, but it's your opportunity to think on your feet.
So, you do?
Yeah, so one thing that we could do to kind of show more the nanoparticle being effective and affecting how this solar panel works could be actually to show maybe more people in the well-working roller coaster to symbolize the fact that more dye is able to bind to these particles that have more surface area per volume. And this could be one way to show how the nano roughness and the surface area actually attributes to the solar cell being more efficient than one created without nanoparticles.
Yeah, they could actually all have people in them, because even the ones with the wrong wavelength could be nano. So that would be a good idea. They could all be full of little people to be the little nano.
Any other questions?
I think as well, the illustrator also showed with the four ramps at the top, he's increasing the amount of carts that are going by, which could also represent nanotech, the use of the nanotech, because it's increasing the amount of electrons that can go through.
Somebody else has to ask a question, or I'll have to ask another question. Come on. One of you guys has to ask a question.
All right, so what we did in this lab was, I'm going to use the very shorthand version of this. So we took some particles and we took some dye, we sandwiched them together.
I just want to know how you measured after you made the cell.
Yeah. So once we sandwiched them together, we held them up in like front of a projector with different color lights. So we had green, white, blue, and red, I believe. And what we used, what's the machine called? Long story short, the voltmeter, we measured voltage and amperage, and then we did a bunch of math and conversions, and we got a number, and then we compared all of our numbers together to get like a line of best fit. Come on, Mom.
Artist, would you please stand up so we can acknowledge you? Very nicely done. Is there anything you want to add as to what was said? They pretty much got everything? Nice. All right. Next group.
I'm Josie, this is Ingrid, and that's Jody. So today we're going to talk about biotoxicity. And so what's biotoxicity? It's basically the biotoxic nature of particles. And so this week what we did for one of our labs was to use silver particles to try to kill yeast cells. And this is, so basically this is really useful in our actual lives because we can use nanoparticles to kill microorganisms, and it can actually save lives.
Okay, so I'm gonna explain this lab procedure a little bit. So basically in this lab, we put yeast cells in different Erlenmeyer flasks and we monitor the number of yeast cells by using a manometer. It's basically a tube and you fill it with a little bit of water. So when the yeast cells do their respiration after they consume the sugar that we put in, they would like either produce some carbon dioxide or they will respirate and then consume oxygen. So the water level will rise or decrease. So that's how we measure. Yeah, and so we basically put 3 kinds of silver into the flasks, which are silver nanoparticles, silver powder, and silver ions. And so silver is toxic, so as it gets to the cell, it ruins the cell membrane, eventually kills the cell. So I'm gonna explain a little bit about all 3 kinds of silver. So we have silver nanoparticles. Nanoparticles are usually 1 to 100 nanometers. So in this case, the silver nanoparticles are the most effective because they enter the cells and kill them by releasing silver ions. And we make silver nanoparticles by mixing 2 solutions, silver nitrate and sodium citrate. And then we'll heat the solution until it turns a faint yellow color. And then silver powder is just silver powder. It's powdered silver, and it has a silver color. And then it is the least effective because the particles are really big, so they cannot enter the cells to kill the yeast cells. And then lastly, we have silver ions, which are silver atoms with a charge. So these ions, because they have a charge, they have to go through special ion channels. So they take a long time. They're not as effective as silver nanoparticles. So we're basically measuring how effective each silver particle can kill the cell. So let's get onto the picture. So here we can clearly see that we have 3 different doors at the airport. And then these people represent different kinds of silver particles. So this guy right here, he is big and he is carrying a bunch of small human with guns apparently. And try not to bring guns with you to the airport, you'll get in trouble. So so this guy basically represents the silver nanoparticles because the silver nanoparticles will carry the silver ions, which will kill the cell. So they're trying to kill people in the airport. So, and also notice how he is wearing a yellow jacket, which is the color of the nanoparticle solution. And then move on to this one. These people are just like these tiny people. So they are just silver ions, and they're also carrying the same goal, which is to kill people. And notice how here the artist points out that they have transparent shoes, which is the color of the silver nitrate solution. And then here, this big guy right here, he is obviously too big to enter through this door. He also carries a gun right there. So this guy represents the silver bulk particle, the silver powder. And notice how he's wearing silver shoes. So it is the color of the silver powder. So so at this airport, everyone is trying to kill people. So so that is what the silver ions are trying to do in the experiment, because they're trying to kill yeast cells. Yeast cells are the people. And then notice how the silver nanoparticles, they can kill the most people because they're the most effective. And then here, this guy kills the least people because he is too big to even enter the airport. And I'll carry it on to Jody.
So this picture
is really good. But one thing that we did in the lab that we saw is that how fast and effective each size of silver particles are. Um, the silver nanoparticles on the left side is the most effective and the fastest to kill the cells, while the two on the two on the right are the slowest. So you might be wondering, why are silver nanoparticles so much effective than the other two types sizes? It's not the smallest, but it's not also the biggest. So what is special about it? Well, the main reason of this is because silver nanoparticles go through endocytosis, which means basically the yeast cell sees it as food, and then it disguises itself as food, and it enters the cell directly and killing it. And this process occurs much faster than just ions going through a different channel and entering the cell a different way. So that's why it's really effective. The other thing is high surface area of silver nanoparticles, because silver ions jump on the cell a lot, and it constantly dissociates and reassociates. So with more surface area, the silver ions are able to be more active and dissociate more, and therefore releasing more silver ions and killing the cell quicker.
Somebody else has to ask a question first.
Hello. Okay. So basically, in hospitals, they use this silver coating to coat their equipment, and it actually it releases small amounts of silver ions, and it helps to. It's basically an antimicrobial coating for it, and yeah, it helps kill cells and
Any other places that you get silver nanoparticles? Can get them?
cancer research.
You can buy Band-Aids, you can buy gym socks, you can buy keyboards. Anything that might get really gross and stinky or get touched by a million people, you can now buy with silver nanoparticles embedded in it. Okay, so I get my question. So you comment that the nanoparticles are wearing a light yellow jacket and that you made your particles yellow. So why are they yellow?
I think it's because of how they absorb the light. Yeah. And so there's something called oscillating frequency. And then when electrons on the particles shift on their electron clouds at a frequency that is the same as the wavelength of the light, it absorbs it and then it gets a color. So it's yellow in this case.
That's good. All nanometals are colored because the electrons can just slosh back and forth and absorb light. So, good job.
Will the artist behind this drawing also please stand up so we can acknowledge your work? Is there anything that you wanted to add in terms of what they said? Is there any concepts that we neglected to discuss? They pretty much got it? Nice. All right. Great. This is the first of our two presentations today on supercapacitors, by the way. So this is one of the groups that had to create their drawing over lunch and then right after lunch go into analysis. So extra props for the very limited time with which to do this.
Hello, I'm Amir.
I'm Herman.
I'm Shahrukh. And today we will be talking about three different forms of energy storage. We'll be talking about batteries, supercapacitors, and capacitors. So supercapacitors, they're a form of batteries that they charge stuff fast, and they charge fast, and they release energy fast, but they don't hold a lot of energy. Then there's capacitors. Capacitors are the worst. They charge fast, but they don't charge as fast as supercapacitors. They also hold the least amount of energy out of all of them. So then we have normal batteries. So normal batteries, they charge the slowest out of all of these, but they hold the most energy. So these are important because in our day and age, we're dealing with global warming. And these are clean and efficient ways that do not emit carbon. So basically, when you use stuff like these, you help the environment. So these batteries are important. Carbon. So how supercapacitors work are you have two pieces of carbon, and then you have electrolytes. So the electrolytes contain electrons and ions. Ions are charged particles. So basically what happens is when you're doing nothing to them, they're just there. You have the electrons inside of the electrolytes. So the first step to charging the supercapacitors, you apply energy to them. Because when you apply energy to the supercapacitors, it forces the electrons to go towards the carbons on each side. Then you apply pressure. You apply pressure because you want to decrease the distance that the electrons have to go to get to the carbon. So the longer you hold it, the more amount of energy you're going to be able to store. So after this is where the discharge process starts. So all you have to do is you have to remove the power source, because when you remove the power source, the ions, they go back to their original locations, and when they go back to their original locations, they begin to produce their energy. So
Okay, so I'm going to talk about the picture. The first of all, we examined that this is a game of dodgeball. And this is a very good example because they've used the balls as electrons and showed how the capacitors charge them. So first of all, this is just a regular, nothing happens, it's uncharged. This is two different charges. This is current. The black ones are current and the white ones are voltage. And they're attracted to two different sides and then shot against the other side. On this is just normal when something is traveling across the circuit from just to the other side.
All right, so let's talk about the limits of this picture. So a couple things. Two important parts of a capacitor are that they charge and then they discharge as well. And here we can see that this is discharging and the electrons are flowing back and forth, but there's no impulse for these dodgeball players to charge. So maybe they could put like yell dodgeball and then everyone starts throwing the balls as an impulse. Any questions?
Okay, so I actually just want to give an idea for this and then let you guys talk another second about the picture. So first I want to clarify one thing, which I think was just said wrong because it was said wrong last week. So normal capacitors charge faster than supercapacitors, but they do have lower capacity. So supercapacitors are in the middle between normal capacitors and batteries in both rate and capacity. So I'd like you to think about the picture, and I could be wrong, certainly have been wrong before, assuming that the balls are ions and the different color balls are ions of different charges. So could you guys maybe say a few words about the picture, assuming that the black and the white balls might be positively and negatively charged ions?
Okay, so in a supercapacitor, when there is a charge applied to it, the ions switch go opposite sides from each other. So at the top they'll be the negative, for example, at the bottom they'll be the positive, and so that's why there's two colors one is positive, one is negative, and when they discharge, they mix back together evenly, and that's why they're throwing it back and forth.
So I'm a little confused about the left. The right I got, or your.
And the left side is a regular capacitor, and it only has one charge ion, which would be, I guess, electrons, which are negative. Any audience questions? Yeah. In a capacitor, capacitors and batteries are different, but yeah, the charges are even. The positive charge and the negative charges in the ions in the capacitor, supercapacitor, are even. So when they discharge, the capacitor is neutral, I guess.
But I think part of the question is, the people look the same, implying that the nature of the positive side and the negative side is the same. In a battery, is the positive and negative side also the same?
For the supercapacitor, at least the reason why they look the same are because they're both carbons on each side, because the electrolytes are sandwiched between the carbon. And for the batteries, I'm not sure because the experiment was on supercapacitors.
By the way, it is capacitor, no capacitate. We got about half and half with everybody here. So, no tay. So actually, I will tell you that in batteries, the two sides are different. They're made of different materials. There's one up there. No, filming.
Dad?
One more thing about capacitors. There's lots of uses in the future for them, for places in like buses, for example. These capacitors charge really fast. So like, Teslas and stuff, they have to charge overnight. Electric cars charge overnight. Buses, for example, that use supercapacitors, they can charge in about 30 seconds, and then they just drive for maybe 5 minutes before they get to a bus stop where they charge again for 30 seconds. And that refills the supercapacitor to full juice, I guess. And that's one of the uses for a supercapacitor, because electric buses, if they stop at a bus stop to try and charge, it'll take a long time to get a little bit of power.
Other supercapacitor group, would you like to describe any sort of additional concepts or clarify your drawing just a little bit for us?
What's on the capacitor one and the difference in people, I totally get. It's really good. On the supercapacitor one. On the capacitor side, there's the people on the left. What's on the right?
Oh, those are also people, but they're just skinny and kind of weak. And they represent different plates, the negative and positively charged.
Oh, so they're the positively charged ones, the ones who lost their electrons.
Yeah, and they're only positively charged because they're relative to the negative side.
Because they lost their electrons. So they're like extra skinny because the other guy stole their electrons.
Yeah, I guess you can do that.
Okay, that totally makes sense.
Thank you, guys. All right, next group.
I'm Rachel.
And I'm Patrick.
We're going to be talking about photolithography. Okay, so the world we live in today is full of innovation. From Tesla's self-driving cars to portable drones, technology is definitely advancing. However, it was not always like this. Imagine loading Google, but the letters in Google loading every 10 minutes. Frustrating, right? Your grandparents or even your parents have probably experienced this loading of Google, like Google's first edition, and from then, the history of processors or transistors of major companies like Google or Yahoo have evolved into the advanced nano-sized ones today. My group and most of society waits for the newest things to come out, such as the iPhone 8 or surgery-performing robots. But these things are here today because of science. And in particular, photolithography is one of the fundamental processes that creates these innovations.
So photolithography involves many steps that ultimately transfers a pattern onto a surface. So just a little brief summary of what we did. So our first step is to place a mask on the surface of a board and place a coating of photoresist. So this will allow the pattern of the mask to be seen when exposed to UV light and a solution. So the UV lights will ultimately weaken the chemical bond and will allow exposed parts to be etched off so you can get your final pattern. And after this is placed under UV lights, a coating of developing solution is placed so that these exposed parts will be etched off and you can get the pattern that was intended for. And so after the etching, the remaining polymer is removed with a stripper solution, so it completes the process and you actually get the pattern. So the picture we're going to describe is the process of actually drawing an actual art and placed in a gallery. So the first painting in the top left is just a blank picture without without the rose or the flower, which represents just the surface with the photoresist solution on it. And then the one to the right of that is with the actual pattern and the board to support the actual thing to support the board. And then the picture in the middle left, it's adding more detail just to prove how intricate these designs are at a closer range and how detailed these patterns will get. So and then in the middle right, it actually shows two different things. First of all, it shows how after using the UV lights and adding the solutions and etching everything off, you get the intended pattern. So as you can see, the support is gone and it's only the actual material that's needed. And then also it shows what happens when it's factored down or scaled down 5 times, which just proves its functionality as seen in the bottom left picture of how the multiple uses of this picture, which is in a locket or above a fireplace. And finally, it's placed in an art gallery to kind of bring a broad topic of a clean room, which is basically in this situation with an art gallery, the art should not get dirty because dust or in this case, any mud or dirt can damage the art. Similarly in our experiment, cleaning rooms are intended to keep dust out and because dust will damage the actual polymer of the surface. And that's about it for the drawing.
So I'll talk to you guys about pretty much how photolithography affects the world. So in the modern days, pretty much everything, smaller is better. And for example, back then, computers, how they were really big and they could only store a few gigabytes. Now, due to photolithography, these chips have been, or technology has been able to shrink them down, and they can contain hundreds of gigabytes, which is a lot more than before. And another example would be in cars and airbags. So back then again, the cars would usually have airbag systems that were positions all throughout the car in order to ensure the safety of the passengers, and this was really inefficient because like again size, and now pretty much they've technology has shrunken down this airbag feature into mini microchips. And for example, if you get in a car accident, this chip could sense if there's enough force, the airbags will be deployed, which is again smaller and more efficient. And this is also a more cost-efficient method too. So yeah. Questions?
Okay, I'll start. All right, so you explained a bunch of aspects of this, and you explained how the experiment worked. So this drawing only captures some aspects of that experiment. So can you please discuss, when I said think about your words, I didn't say don't talk about the limits of these drawings, because they all have limits. So could you talk about what aspects of the experiment, particularly like the really key aspects, are not captured, and how you might include them in a drawing like this?
So one thing that we particularly noticed was we did not see a transition with the UV light and the idea of coating, like coating after UV lights, coating with a developing solution, which a quick solution of that would be just adding a light over the actual portrait while working on the portrait to kind of demonstrate how there is actually a light there in like the middle two drawings.
What about the concept of pattern transfer?
Hold on.
Convene. Mumble, 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 mumble. Talk. The idea of pattern transfer. How might you add that in? So what specifically would represent the mask in this drawing?
Well, it could be in the first photo in the top left. You see, it's kind of hard to tell, but that little shaded portion on the actual portrait before the pattern is there, it's like right. It's in between. It's hard to tell, but if you looked at the actual drawing, it's there. It's like a little like like shading sort of. So that's what we thought it would be.
Okay, so there's actually a pattern on the first one.
Yeah, it's just kind of, it's hard to tell, but if it's on the actual paper, there's a little pattern.
Just a base coat. Which one do we have 3 of? Okay, so I get one more chance to get all the concepts across. Okay, then you only have to have part of the concepts there. Okay, so let's do some other questions.
So it's pretty much in the lens where first you would start off like with a bigger design, and then you would use like you would shine a light through it, and you would use the lens to bend the light, which will then project the image, and like pretty much it would go like this direction, like the light, and then it'll just pretty much just shrink the image down, and then you just go through the same process as this, and you'll get your product pretty much. Yeah. Yeah, exactly.
Okay, so can you get as small as they really are just using a magnifying glass? And if not, why not?
That's a good question.
Yeah.
All right, well, start first. The first one's yes or no, so you got 50% odds. Can you just, is a magnifying glass enough to get down to current Intel chips?
Probably not.
Okay, no. Any idea why not? What's the limit of what you can do with light?
Isn't it like half the size of the wavelength?
Yeah, it's some function of the wavelength, and it's bigger than what you're currently getting. So they do focus, and then they also do all sorts of other crazy, weird, stupid things, like they have patterns that are overlapping patterns, and only in the little region where they overlap do things get fully exposed. So light enough in a magnifying glass is not enough to get as small as they are. You have to play a lot of other games that I don't even know all the details of. But just be aware that just a magnifying glass is not sufficient to get to what is current chip size. They're in the world of really crazy games with light to do that lithography.
Artists, would you stand up so we can acknowledge you? Is there anything that you wanted to add to what was said about your work?
No, I think I did a pretty good job of getting all the analogies. It was kind of hard to actually, in this analogy at least, show the actual steps of the photolithography process, so I just tried to show that there were steps in place.
Yeah, this is really one of, for me personally, I think it's one of the harder ones to do in terms of a visual analogy. So yeah, this one is definitely a challenge, for sure. But nice job. All right, next group.
Hi, I'm Ashley, this is Jane, and this is Alan, and today we're going to be talking about hydrophobicity and also hydrophilicity, which is basically, so hydrophobicity is the property of a substance being water-hating, and hydrophilicity is the property of a substance being water-loving. So hydrophobicity and hydrophilicity are very important and seen in common uses in medical situations, and there's even planes that that incorporate hydrophobicity to not get frosted, and they're also, and even in clothing such as raincoats and shoes that are stain proof.
So before I talk about this picture and analogy, I just want to, highlight 2 points. So how water interacts with the surroundings, especially a surface of material is depending on mainly 2 things. The first thing is the chemical functionality, meaning that if or not the water and the other material has similar chemical properties, and the other thing is if the surface has nano roughness, meaning that if on the nanoscale, if the surface has many bumps and a lot of surface area. So if the water and the surface have the similar chemical functionality, then the water tends to be hydrophilic, meaning that the water wants to stick on the surface. So imagine on paper, if it's hydrophilic, then the water tends to spread on the surface. So one way where we can measure this is through the contact angle, meaning the tangent of where the water meets the material. For a hydrophilic material, it's usually a very small angle, and that's the opposite for if the surface and the water has very different like chemical properties, then the water tends to beat up because it's kind of like repelled by the surface. So like in this picture, this part is kind of this picture shows basically how people interact with pigs and porcupines. So like in this picture, like this girl is hanging out with these pigs and they are getting along with each other. So, and especially so from here we can see, and because they are getting along well with each other, so it kind of shows that it's an analogy to just the normal hydrophilic interactions. And we can see also from this picture that because there's like a arrow here, it kind of symbolizes have a small angle. So like for a normal hydrophilic surface, like the water tends to spread on the surface, but it's not like completely spread out on the surface. And so if you have like some nano roughness, meaning that you have a lot of surface area, like in this case there are like two pigs hanging out with this guy and they are getting along well. So I guess this guy is kind of, I don't know if it's lying on the ground or anything. So it kind of shows this is the super hydrophilic example, like in analogy of how people interact with pigs. And for the hydrophobic part, and we can see this like the porcupines and this person is kind of, they're disturbed, I guess. And there's also an arrow here symbolizing that the water is like the people is kind of bending outwards. If you think about if that's a water droplet, it's kind of like it's speeding up. So that's an example of the hydrophobic behavior. And on this example, like this girl is curling up, and it's like similar how a water droplet would behave on I don't know, like a lotus leaf or anything. So like the water beats up on this kind of like hydrophobic surface. And there's also like two porcupines, meaning that there are like little bumps on the surface, and there are two of them, so like more surface area, I guess. And also like the porcupines have like spikes on them, so it's also, I guess, shows the nano roughness which is required by the hydrophobic surface. Yeah.
This picture is really nice and cute, but I have one limitation is that besides roughness, we need chemical functionality, which is about polarity. When two things are the same polarity, they tend to stay together, and when they have different polarity, they repel each other. So I think we can represent that by like same gender of the animal and the person. So when they are same gender, they like each other. When they are different gender, they dislike each other.
So it has to. I think it has to do with like the structure of the surface. Imagine if that's a surface, and if it's like super flat, and if it's hydrophilic, meaning like if the chemical properties is similar, so the water still has a lot of contact areas. But if there's a lot of bumps on the surface, so what the water drop is actually in contact with the surface, it's actually very small. And if it's hydrophobic, so and the air that's trapped between the bumps is also kind of making the droplet a spherical shape. That's why the water beads up. And if it has like some structures on the surface and it's rough, and then if it's hydrophilic, then the water has more surface area to stick on the surface. So like so basically the roughness of the surface make the hydrophilic, more hydrophilic, and hydrophobic, more hydrophobic.
So one thing I see here, so we've got, so for the hydrophobic and hydrophilic, we've got one animal, and for the super, we've got 2 and 2. But one other thing I noticed is that the porcupine actually, he does have more surface area when it's super hydrophobic, but the pig, I think, kind of has the same surface area, even though there's 2 of them. Is there maybe another animal that you could think of that could have a high surface area as well? Similar to how the porcupine is rough, is there like a rough animal that would be like nice to pet that would be hydrophilic?
I guess like a turtle would kind of be.
I want to meet your rough turtle. Chinchilla. Yeah. Okay, I'm going to ask a different version of a question. So what you explained is very good. It's correct in terms of the way that roughness amplifies hydrophobicity or hydrophilicity. If you're hydrophobic and you're rough, you will not wet the whole surface, so you're really just going to touch the tips of the roughness, and so then you have a surface you hate and you don't have much surface area. And if you're hydrophilic, you're going to wet all of that hugely increased surface area, and so the droplet is really going to spread down. So that's a concept that's not captured in this picture. And so now my hard question, and I don't have an answer, is how could you start to capture that concept? And that's the hardest thing. Nobody's pictures, not across all the camps, not just this one, have been able to capture that concept in a picture. How might you start to modify that to think about getting any aspect of that concept in this picture? I could think of, there's some ways you could modify this picture.
So I don't know if that really makes sense, but so for the pig, like you kind of can like hug over it, so you have like a lot of more surface area to be intimate to the pig.
Yeah, no, exactly, exactly. You could be, and you could be not hugging or just touching the tips of the spikes of the porcupine, and so that concept of really touching the surface area in the hydrophilic case and not touching the surface area in the hydrophobic case could actually be incorporated. In many cases, once you start really thinking about it, you're like, oh, wait, I could change it. I could add this concept. And that's when you're really making cool science analogies. So good job.
Would the artist of this very adorable illustration please stand up? Nicely done. Is there anything that you would like to add to what was said? Yeah, I really liked that one, which was why I asked the same question for could that be done with hydrophilic, right? Because you showed that really well with the hydrophobic ones, that there is a difference in roughness. So it would be interesting to try to do the same thing with the super hydrophilic. And it's not easy to find an animal that you could do the same thing with. So, which is why I asked.
Maybe some fur you could bury your hands in so you could touch all the super hydrophilic surface area.
Yeah, I would when I was thinking about it, I thought of maybe like a baby sheep and then like a fully grown, really, really fluffy sheep. So like the fluffy sheep has more fluffy surface you could touch. But even that's like not great. Like the hedgehog one was really good. So again, hard to find one for the hydrophilic, but very nicely done. All right, next group.
Hello, everyone. My name is Megan. This is Jen, and this is Jamelyn. So today we are going to be discussing the applications of nanotechnology within dye-sensitized solar cells. So did you know that only 9% of the energy we use is renewable? Finding renewable energy is important because we need some energy source that can power our world once we have used up all our non-renewable resources. So essentially, dye-sensitized solar cells are a piece of nanotechnology that captures the sun's energy and converts it into electricity. So normal solar cells use silica and expensive dyes and other chemicals that capture the sun's energy. The cell we made in our lab was much cheaper because we used transparent conductors and fruit dye made of raspberries. While it was not the most effective solar cell, it's still impressive how we were able to obtain some energy from cheap materials, and with more research, we can find more ways to make these solar cells even more efficient.
So you guys might remember how the other group that did solar cells, their picture depicted a roller coaster that kind of, some of the roller coaster could work, some of it couldn't, but it didn't really depict how the roller carts, the coasters, went around the track and the different steps. But what this image does really well is depicting each individual step. So just in more sciencey terms, the way that the solar cell works is there's a sandwich between the two transparent conductors, and in that sandwich there's iodine, which provides electrons so that the electrons don't run out, and there's also dye, which absorbs sunlight. And when the sunlight is absorbed, it excites the electrons. And because they're excited, they move from the dye to to a layer of titania, which is like a conductive type thing, and through like nanoparticle bridges that it can use to jump between the dye and the titania. So from the titania, it goes to wires, which send the excited electrons back around to the beginning of the solar cell again, making a full complete circuit or circle. So in this diagram, the first thing that's really clear is that it's a complete circle. So the electrons, which are represented as water in this, can go all the way around and then are brought back and then steam up and then continue the cycle. So it's constantly replenishing. In this image, this big pool of water is the iodine. So it's making sure that the water doesn't run out because it's providing extra water to be used. So from there, the sun in this image is represented by wind power instead. So the wind is powering all of these little wind turbines, which are the dye because they're absorbing the energy. So when you're designing a solar cell, you have to find a balance between current and voltage. Current means there's like a lot more electrons going through, but they're less high powered. So that's represented by these little tiny windmills that are getting a little bit of energy, but they're not getting as much as a single big windmill, which is voltage. And so another concept that they represent is when you're using a solar cell, some wavelengths of light work better than others. So like if we had a red dye, green light proved the most effective because they're complementary. So here, this is the one that works the best. This amount of wind power, because it sends it right up to this platform. When you have too much wind power, it goes way up high, it misses it. When you have too little wind power, it also misses it. So that represents how the power of the wind is only certain amounts of power work. So from the, here I want to make sure I'm getting it. Okay, so this top platform is representing the titania because it's taking the water, the electrons, and it's transporting it to the beginning of the cycle again, and where the cycle restarts and continuously goes.
Okay. Something that this cartoon could emphasize even more on is the aid of nanoscience, which is that the electrons where the electrons can find a really quick, direct path between the dye and the titania layers before it loses the energy. and falls back down to an unexcited state. And another concept that we learned about is for controlling the film deposition, where we used, what's it called? Spin coating, which provides a thin layer of titanium, which is made from preventing gunk from intercepting the reaction. Questions?
Okay, I'll start. All right, so up at the top, there's the water gets pumped up, and then there is a wheel. So I have two questions for you. One, what is the wheel, and what does it represent? And then two, I think that the big C is not the iodine. I think something else in the picture is the iodine. And so I'd like you to maybe try to pick something else that you might associate with the iodine.
Okay, I'll give this my best shot. So first of all, with the water wheel, because water wheels are usually like for collecting power, I think that might be representative of how with the circuit, the whole point of getting the solar cell is that we want to generate power or electricity that we can use. So this kind of represents how when at the end of the cycle, what we're producing with the electrons moving is we're producing energy that can be used.
So that's the work that is done as the water goes back down.
Mm-hmm.
That's the work that the solar cell does. Yeah.
And with the iodine, because it's providing electrons or electrolytes that continue with the cell, then maybe it's the people who are refilling it because it's preventing it from, this small pool. If this continues going without these people to connect it, they're going to run out of water eventually. The pool's going to dry up. So since they're replenishing the pool with more water, then that's probably the iodine.
That's exactly right. The iodine is a shuttle to just bring electrons back from one electrode back to the rest of the system. And they're your little shuttle, shuttling your electrons back. Good job. Now somebody else has to ask a question.
I know you're filming. Do you want to ask a question? Oh. Okay. So that's actually something that could have been represented in this image is when the electrons get excited, some of them get excited enough that they can continue through the cycle and produce electricity, but some of the electrons aren't excited enough that they fall back down, like with the roller coaster, the cars fell off. So here, there could have been like a little bit of water kind of, oh, there actually is, I didn't even notice that. Okay, so there's like water spouts coming down. Those are the electrons that didn't get excited enough, so they fell back down. And when they fall back down to their unexcited state, they release unusable photons of light. So they kind of shine light instead of producing electricity. So that's kind of what makes LED bulbs work, is that they're not getting excited enough, instead they're falling back down and emitting light. Okay, so I'm gonna try and remember. I think I got this. So one way that you can make the cell more efficient is if you're able to raise like the metaphorical level of the platform. When it falls down, again, it's going to be releasing more energy. So that's one of the problems with our dye sensitive ones, is that you can't really excite it too much and get very much usable energy back. But with silica, you can kind of excite it to a higher level so that when it falls back down, you release more energy, I think. So
what you're saying is right. So what is the word that we would use to describe the height? What is the thing you measured that is related to the height? Any of you guys? It's not like some weird esoteric thing. It's one of the normal things. Any of you guys? Your team? Just try. And no, this is not like some weird. This is not some weird term. This is like a really common thing. Well, what did you measure about your cell? You didn't.
Voltage?
The voltage. Yep. The height is the voltage. And what's the current?
Current is the number of electrons passing through.
So in this picture, it's
In this picture, the
current would be what?
current are these guys, or no, it's the
Current's it's part of the cycle. So the voltage is how high it is.
voltage is how high it is. Water current is how much water is coming down.
Exactly.
Okay.
Exactly.
Okay. We got it.
Artists, would you please stand up so we can acknowledge your work? Are they here? Did they have to leave? Oh, they might have had to leave. That's unfortunate, but let's give them a quick round of applause for their work. I think it was Alan. All right, so next group.
Testing. Hello, everyone. Thank you for coming today. I'm sure you're all on the edge of your seats to learn more about nanoscience. My name is Mishan, and here are my partners, Brandon and Christian. And today we're going to be talking about the varying levels of toxicity of different sizes of silver on yeast cells. So throughout this presentation, you'll learn that the smallest differences in the sizes of silver particles will have a significant effect on the yeast's health, which is measured by cellular respiration. For example, silver ions, the smallest type of particle in our experiment, are less than 1 nanometer in size. Silver nanoparticles, the medium-sized form of silver in our experiment, are somewhere between 20 to 50 nanometers, and bulk silver is in the micron range. So evidently, even the smallest differences in the sizes of silver have a very significant impact in experiments involving nanoscience. In fact, we're so accustomed to learning about these tiny, tiny particles that particles such as microns seem huge to us now. So the question is, why should you listen to us ramble on about microscopic silver particles? Well, silver is everywhere, and it's found in bandages, jewelry, circuit boards, water filters, etc. But this specific application of silver in nanoscience heavily contributes to important topics such as cancer research because it enables us to target specific destructive cells in the human body, and it allows us to kill them without doing any harm to the rest of the body. So to learn more about the process of killing these specific cells, I'm going to turn it over to Christian.
All right, guys, so is this on? All right, so as you can see up here, there are 3 different computer screens, and on them there are 3 different images which represent the various sizes of silver. So on the far left, we have the nano-sized silver because, well, this type of silver actually causes the most damage on the cells, as you can see, like all the cracks. And in the middle, we have the bulk silver because it causes the least amount of damage. And on the far right, we have the silver ions, which cause like a medium level of damage. So the intruders and like the various houses that are like breaking in represent the silver particles in the experiment, and the house represents the cell because it's being attacked by the intruders, which represent the silver. And the various vehicles that you can see in these like little bubbles outside the house represent the sizes of the silver outside the cell. So basically the nano size silver is shown to have like a bike that brings it to the cell, and it's like the medium-sized method of getting to the cell because the car is larger than the bike, and that's the bulk silver, and no transport is smaller than a bike, so it's the silver ions. And then you can see that the silver enters the house through various openings. So on the very left, you can see that the silver ions are entering through the door, which represents how the cells take in the nanosilver through a process of endocytosis. So basically, they mistake the silver nanoparticles as other objects, and the cell membrane kind of wraps around them and brings it into the cell, where then the ions can damage it. And then in the middle, you can see the bulk silver is like too big to enter the cell, because like there's no openings or ways to, because the cell is so small and the bulk silver just can't get in. So what happens in fact is small ions break off outside of the large bulk silver particle, which is outside of the cell, and like very few of them can travel through special channels for small particles and do a slight amount of damage, which you can see like there's only one intruder damaging the house. And on the far right, the silver ions are entering through the door, and the reason why there's only like a small amount of cracks in the house is because the window is a lot smaller than the door, so they can only go in through like a slow rate. So the damage occurs more slowly. And the damage done to the house represents the level of toxicity that the silver has to the cells.
So I think that this drawing did very well at showing the concepts that the artist decided to show. But like all drawings, we can't show everything. So there's one concept I'd like to point out, and it's how the nanosilver particles, which are represented by these on the left, when we used them in our experiment, they were yellow, and maybe we could have shown that by coloring each of the intruders in the house a different color. And I guess since the time is up, thank you for listening.
Any questions? Yes. Artificial intelligence to our nanoparticles. Possibly, if we want to further this science with cancer research, we can make nano-sized robots to transport these ions to these cells, to specific cells, to destroy these cancer cells. That's one way we can incorporate nano-sized silver. Yes. Yes, I think so, because, yeast cells specifically undergo cellular respiration. So when all these different forms of silver get into the yeast cell, they basically catalyze the formation of reactive oxygen species, which is basically inhibiting their ability to consume oxygen, thus killing the cell. So I guess it could be dangerous if this reaches other cells and kills healthy cells.
Are we putting you in danger in this nanoscience camp?
No.
Correct. So why?
I believe that we learned in one of the lessons that the human body has like various vitamins that help protect it against the silver, or prevent the cells from becoming damaged.
I think part of it is actually just that the silver particles don't get into the human cells the same way, but also it has a bunch of different enzymes than the yeast systems, because it is a very different organism. But I think a lot of it is just that the silver particles are not eaten by human cells the same way they are eaten by yeast cells. So what would happen to you, here's a question, if you ate silver nanoparticles?
Well, I think we learned from one of the instructors that our body actually has antioxidants. So I think our cells would probably handle the silver nanoparticles better than how the yeast cells did.
Yeah, but something does happen to you if you eat large quantities of silver
Oh,
nanoparticles.
we would also turn blue.
Yes, you would turn bright blue. But otherwise would be very funny looking, but relatively unharmed. Apparently. Don't try this at home. We're not condoning it. Okay, so my question is, as always, there's a limit to every analogy. So there's something fundamentally different about the nature of silver ions than about the nature of the nanoparticles. And what is that difference, and how might you reflect that in this picture? I mean, and it is actually sort of reflected, but how could you reflect it more?
Well,
share the mics around so that everybody gets to answer questions.
So I think what you're referring to is the different means of the different types of silver in getting into the cell. So, for example, if you're talking about bulk silver, it would have to dissociate outside of the cell, and all
It dissociates into what?
Silver ions.
Which have?
Charge.
Charge. How could you maybe reflect that?
Some sort of visual element showing that they're charged or something, like to set them apart.
I don't have a good answer. These are your opportunity to be creative. But the people all look sort of like the same people here. And in fact, neutrals and ions have very different interactions with things.
Right. So maybe that could be depicted in a difference of emotions between these people in the picture, which would show if they're positively charged or neutral.
Yeah, potentially. Anything about the looks could potentially be used to sort of depict that difference.
Everyone keeps turning this one off. Well, the next group is coming up. Artist, would you like to stand up so we can acknowledge you? Is there anything that you would like to add to what was being said? Yeah, so I guess the method of transport is the size and what they are, but they're all ions that are killing the cells in the end. So I guess all the people are ions, but then the bike would be the nano, the car would be the bulk, and then just the people are just the ions in that case. Very nice, thank you. All right, next group.
Hi guys, we're Team 10, and I'm Josh Zoe. This is Ayush.
I'm Ayush.
And this is Elliot. Now, I was asked to open, so just going to start with a little demonstration. So, surprisingly, most of you guys have an iPhone. That's not surprising. But what is surprising is this is a perfect demonstration of both a capacitor and a battery. This is basically what we talked about this morning. So, it's a battery usually, but when you go to the photo and turn on flash, it becomes a capacitor. It discharges electrons almost instantaneously. So basically, batteries are the transfer of electrons in chemical reactions called redox reactions, and we use that to power devices. On the other hand, capacitors work on a different scale totally, using two different plates and charging one with electrons, and then as soon as the circuit opens, the electrons flow out. Now, you use both of these for completely different functions. Like, you wouldn't want an iPhone battery with a lifetime of like maybe at most 2 hours, and you wouldn't want an iPhone flash with like a 2-hour-long flash, but only like minuscule power. But what if you want something somewhere in the middle? what if you want something like a bus battery that lasts from one stop to the other and you can charge it at every single stop? Something that charges fast, a little slower than a capacitor, but faster than a battery, and has almost as much almost as much electrical density as a battery, and that's where the capacitor comes in. I'll turn it over to Elliot.
All right. Thank you, Josh, for that. So now we're gonna analyze this picture, this beautiful picture. How do I turn this on? All right. Okay. There we go. So this picture actually takes place in the hood, which, if you don't know, is basically the ghetto, and a lot of stuff goes on in the hood. So there's look here. There's people standing between the street and the wall, and people represent electrons. And then, since they're doing sketchy stuff, the cop comes over, and then the people scatter. They go back to the wall, and that kind of represents a capacitor because basically the police, they charge when they come. They make the people, the electrons, go to the other plate. It's kind of how a capacitor works. And then if you go down, there's a bigger hood, and this one has two buildings instead of the cop car and the wall. And this one basically has a bunch of people standing there, kind of like the dodgeballs in the other picture. And when the cop car comes, the people scatter, and they go to both sides in this case because it's a super capacitor. And as Josh mentioned, although this one may have more power than the supercapacitor, this one does compromise some of that power for a longer lasting energy source. And now, Ayush.
So I'm gonna tell you what's like good about the picture and what I thought they could have done better. So I like the way that they show how when the cop car comes, which could be signifying the electrolyte, it comes and disperses each ion to the sides like a capacitor. But the only thing is they never showed the ions coming back and shooting, discharging it. And in the top picture, it looks like there's only one plate here, and the problem is with capacitors, there's no electrolyte, so the cop car doesn't make as much sense. Any questions?
Okay, so what do you guys think the cop car is?
Electrolyte.
I think that's not it.
The cop car is like a signal almost.
Okay, so what in your experiment is the cop car?
It would be the moment that we press the button twice.
And what happened when you pressed the button?
It opened the circuit, and so the electrons started flowing past.
So what is the cop car doing here?
It's essentially sending a signal to the street, the side of the street, which makes the electrons go to the other side, the other plate.
But in people, you send a signal and then they can decide to do something because they have a brain and they can take information and act. But chemical systems have no brain, and so a signal is not necessarily enough to force something to happen.
But basically, the reason why they made this take place in the hood was because statistically speaking, a lot of crime happens in the hood. And when a police car usually shows up, the general instinct is to run away.
This is all good, that's fine. But in your experiment, so the cop car is not a signal. The cop car is the thing that's making the electrons move. What's making the electrons move?
So in a capacitor, a supercapacitor, each side is charged differently. So one side will be charged positively, and the other side will be charged negatively. So
this charging thing you speak of, how do you do it?
So the problem is the police car actually acts in this picture as a positive force, like forcing them to move, but
It's a
actually
force.
Yeah.
What was your force in
There
your
was
experiment?
no force because
There,
actually
of course there was a force. Nothing happens without a force.
in the capacitor, the force came when we were charging the plates, when we were pushing the electrons to one side, pushing the ions to one side or another, and then when you let go, they all ricochet and then disperse themselves again.
Okay, yes, exactly. That was excellent. So, in this case, what is the thing that is forcing the in your experiment? What is the thing that forced all the ions to one side?
The potential difference in the current in the
voltage. Okay, so the cop car is
voltage.
Yes.
Right.
Okay, so now my next question is, the people are not the same things in the two experiments. How are the people different?
So a capacitor and a supercapacitor are kind of similar in concept, but they work pretty differently. So in the first one, people kind of represent the electrons, whereas in the second one, they represent ions.
In the first one, also, all the electrons are the same charge, but in the bottom picture, well, the plates are one charge, but in the bottom picture, there's different charges. Each plate is a mixture of different charges.
So, right, electrons only come in one flavor. So you can only have electrons or lack of electrons, but ions you can have positive and negative ions. So in this case, you'd say people are all charged things, even though there are electrons in one case and ions in another case. Okay, good job.
Thank you.
Now other people have to ask a question. No, you can't clap yet. Somebody else has to ask a question.
Oh, nice.
Well, see, that's where the nanoscience comes in, because in a regular capacitor, you have one, like there's. Well, I would say that that was because in a regular capacitor, only one side is doing the action, while in a supercapacitor, both sides are either gaining positively charged electrons, positively charged particles, or negatively charged particles.
Also, I think it's to show that in the first one, in the capacitor, each plate is different, but in the supercapacitor, they're similar.
They don't really have any specific name, that I know of. Oh, they do? What's the term? Positive plate.
No, because usually a capacitor is like two plates of metal or And Eric, you had a question too, right? Well, you would increase the surface area because that would allow for the storage of more electrons.
And in the picture, what would that be?
A longer wall or more
more
like
buildings.
higher apartments.
Or more buildings.
Higher apartments is the way, because the whole point is in a parallel plate capacitor, you can't really increase the density per unit area. but in the supercapacitor you can't. So higher apartment buildings would be the perfect way.
Thank you.
While the last group makes their way down, artists, do you have anything to add to what was being said about your drawing? Yeah, that's the tough thing about doing a visual analogy is that if the difference isn't exaggerated, it can be very hard to see.
Yeah.
So
So in reality, the difference between a supercapacitor and a parallel plate capacitor would be like a 100-story building. It's like a lot more surface area, but it's a very good way to show the differences.
yeah, for sure. So nicely done. All right, last but not least.
Hello, I'm Madeline, this is Bruce, and that's Abby, and we might not be as interesting as the hood, but we are going to talk about photolithography. So photolithography is basically when a mask is made, printed, and then light is shined through normally high energy light like UV or X-ray light, and that will create some kind of intricate design onto this chip. And the chip normally contains a substrate and metals and other materials that when different stripping and etching goes on, it will come out with a chip that can be used in computers and CPUs. And that is very important in today's day and age because we can use nanotechnology to try to make those masks smaller, which eventually makes those chips smaller as well, allowing us to have smaller phones and computers. And as we decrease the chip size, the distance between different components in the circuits also decreases. And this can be good, but then it also can increase the resistance because the wires can get thinner. So as developers make these new chips smaller, they have to take into account the proportions and that they eventually want to come out with the greatest power input.
Cool. So, Madeline, I'm not sure if I mentioned this, but the artist makes a really good analogy of using photolithography in baking a cake. So, as you can see, first you have to gather the ingredients and assemble them. In photolithography, what you're going to be doing is you're actually going to be layering things. So you're going to have a substrate, a conductive metal. We used copper in ours, but it could be any conductive metal or semiconductive metal. And then a photoresist. Next, you're going to put the cake into the pan. Or if photolithography, you're going to put a mask on it. And this mask will cover up the area that you want to be like the design or the wires. So that would cover that up, and then the cake goes in the oven. In the photolithography, your little chip is gonna go under UV light. The UV light will cause a chemical reaction to happen between the photoresist and all the uncovered areas of the photoresist, which makes it then possible for the next step to happen. So after you take the cake out of the oven, you're going to trim it. So you're going to let it out to cool, you're going to cut it up, and you're going to cut off all the burnt stuff. In photolithography, this is sort of the process of developing and etching away all the photoresist and the copper you do not want. So when you're cutting the cake, it's kind of like developing the design. So when you put your photolithography in a little thing, it will cause all the excess photoresist to fall away. And then you will then cut off all the conductive metal that you do not want because that will mess with your circuit. Finally, you ice your cake or you strip your metal. So then after you have a design, which is just metal and photoresist, you just need to take off the excess photoresist and you have your little wires. So lastly, you eat the cake, and this is actually when you use it. You may have noticed earlier, but the artist makes two cakes, one with like 3 little things and one with a lot of smaller things. So this is sort of talking about how we can use nanoscience to make these. So The smaller one is able to be eaten faster in 1 minute, as this person says, even though it's the same amount of cake. This is because when things are smaller and they have more surface area, as it always is in nanoscience, it's a lot easier to use. That's basically the process.
All right. So one limitation of this drawing, it is briefly mentioned, but it is not one of the primary features, is the need to use, in the case of the analogy, a clean baking pan, or with, in the case of manufacturing microchips, it's using like a clean substrate, because when you're looking at the scale that we're currently producing, which is on, like, the current feature size of most microchips is around 14 nanometers. So at that scale, even the smallest piece of dirt or contaminants will cause an immense problem when manufacturing. So we use a clean room, which is just a contaminant-free room where we can produce chips that have up to a 99.9% yield, meaning that 99.9% of the chips that come out of that clean room are useful. Questions?
So the big thing in making chips like this is resistance. And when the current has to travel a longer way, that is more resistance. So when it's a lot bigger, that's more resistance and it's slower. But the issue is when you're making things so small, the wires are also getting thinner, which also adds more resistance. So Madeline kind of touched on it, but it's finding a balance of making it small enough so it's faster, but not, the wires can't be too skinny or else it'll just be too much resistance.
In addition to that, when you look at, once you get to very, very small features around the order of about 5 nanometers, you don't always have control over the flow of electricity through those transistors, so that can cause problems, because if you can't control it, the chip is not going to perform the functions as it should.
The transistors do also get much faster as they get smaller.
Yes.
Okay, so I have a question for you. So now I get the question that I didn't ask last time. Okay, so first, what is the mask in this picture? I think you guys said it, but
it's the
Cake
pan.
Okay, so what key aspect of lithography is captured in this picture with respect to the mask?
That it takes the shape of the object or the pattern that you're trying to print onto the substrate.
Yes, but but other ones, like with the picture and the other pictures, there was that concept was there, but there's a concept here that is pretty explicit with respect to a pan that hasn't been in some of the others.
Is it possible?
Tell me about your baking pans at home.
Well, I mean, we have
Stick
two
or
different sized
non-stick?
baking.
Stick or non-stick?
When you want to bake a cake, what do you do?
Oil it.
You know, you just
Pour the batter in the cake pan and then put it in the oven.
Yeah, and okay, and you do the whole thing, and then you're done, and what do you do? And then when you're totally finished,
Get out of the pan.
you're totally finished.
Wash the pan.
Okay, and then after that,
Cake.
Use the pan.
reuse the pan. Okay, so what aspect of photolithography is captured really well in this picture?
You can use one mask over and over and over again to make multiple.
Of the same thing.
That's the key concept. The mask is really expensive to make, but you can use it again and again to make the exact same cake or the exact same pattern repeatedly. And that was the one concept that we had gotten before, so I'm really glad I waited until this picture came around. Okay, so now I have a second question. So the cutting off the burnt part is the stripping. What is the frosting? I'm sorry, I just can't figure out.
Actually, the cutting off the burnt part is the etching.
That was kind of one of the limitations of this drawing. I heard the timer, so I wasn't able to completely get into it. Is that obviously with these analogies, like you said, it's kind of hard. You don't really like ice the cake and then cut it off. So in reality, it's kind of, I mean, the process is basically reversed, but that was kind of our, this was like, to the extent the analogy was able to explain the process.
So I guess I would say that basically the dumping the cake out of the pan is sort of the etching, because that's where you end up with the patterned cake that reflects the pan. And then, the little burnt part is the stripping. And then, I'm sorry, I'm afraid you might have to eat unfrosted cake. It doesn't taste as good, but...
I have an interpretation, and actually, also, I have an interpretation, and I like your team to maybe answer it. So relate the let's assume that the eating, right, the two figures in the bottom with the 1 minute suggestion of time, etc. If let's assume that the suggestion is that this is a function of the cake, meaning the value of making that cake is the cake itself, and maybe related to the icing. So with that kind of connection, would you be able to say what might be the illustrator or the artist trying to say about the icing? What might that be related to your experiment?
Or not actually related to your experiment, but related to the
process. Or process, or how technology is used like this. If you add a layer, and that layer is part of the function or a useful thing, like eating it tastes good.
Well, one thing that we looked at, and I'm not sure if this is quite the direction you're going, but when we were looking at lithography, we're also looking at other uses for it. So especially with different methods like soft lithography of making actual nanostructures, where in order to make a specific structure, you make one little layer, and then you etch it out, and you make the pattern that you want, and then you put another layer on top of it, and then you etch that, and then slowly you can build up a full-size nanostructure.
Yes, so I think one interpretation of this is that the icing itself is one of the functional material structure that this illustrator wants to say. It could be, a structure of plastic, or in your case, perhaps the metal itself.
But a transistor is not just metal. It actually has multiple metals and semiconductors. So this could be more part of the...
It's okay, I can turn it back on. But thank you for letting me know. Before we conclude, artist, would you stand up so we can acknowledge you? Nicely done. Anything that we missed that you would like to add? Everyone pretty much got it?
Okay, so what did you intend the icing to be?
So the icing was just another layer, because you can do a layering thing with photolithography. All right, cool. Well, let's thank all of our presenters for doing a really excellent job. Again, this is no small feat to take what you've learned in a very short period of time and come up with these visual analogies, and then try to talk about somebody else's analogy and really explain the science behind it. So well done to everyone. I think Dr. Tolbert wants to say a concluding remark before we end.
Okay, you guys were great. You made it through all my questions. You're allowed to take freshman chemistry now. Before we end, I want to just say thank you to all the parents for giving us your kids. Sometimes it's hard to give away your kids. Sometimes it's easier. It depends how old they are. My kids are getting there, trust me. So I want to thank all the participants. You guys did great this week. And I really want to thank Rita, who has been the organizing force behind this whole week camp. And so let's give a big round of applause for Rita. Okay, so I believe at this point we have a reception in CNSI, but just before that, for those of you who were staying at the dorms, what time, 6? 6 o'clock. So for those of you who were staying at the dorms who left your stuff at the dorms, the room where your stuff is closes at 6 o'clock. So you have plenty of time. It's only a little after 4 right now. But do remember, if you want to go show your parents all around campus, you need to be back at the dorms before 6 o'clock, or your stuff will be locked up for the night, and you will not be able to get it back until, I don't know, maybe tomorrow, maybe on Monday. I'm not sure when. So please keep aware of the time. All right.
And one more thing, so before we all go inside CNSI to enjoy the reception, we would love to get a group photo of all of you guys before we go in. So let's actually meet right outside of CNSI under the sign that says California Nanosystems Institute, so we and your parents can take lovely photos, and then we'll go inside.